Hello. Hey. So I work at Shopify, and I'm going to talk to you about some simple scripts that we wrote to navigate our data warehouse and the Unix tools that we combine them with to get the most out of them. In case you haven't heard of Shopify, we provide a platform for people to sell products online or in person. We host their e-commerce websites, and the specific team that I work on develops software for and maintains a data warehouse, or a platform used to collect, store, analyze, and report on data from our systems. And our analysts use it to answer questions about the performance of Shopify as a business, our products, or our features. For example, one question we try to answer for Shopify as a whole is, what is the total value of everything sold through our platform, or the gross merchandise volume? That's one of the metrics that we use as a company to gauge our success. To make this chart, we first create a data set with one row per order transaction. And this is not a trivial data set to create given the volume of orders and transactions that we process through our e-commerce websites for our merchants, and what we join this data set against to be able to break it down by payment gateway, the industry of the shop, the monthly recurring revenue that they generate for us, etc. In 2016 alone, we had over $15 billion worth of GMV. That's a lot of rows in some databases. We're also continually processing data to keep this data set up to date. But from a broad technical perspective, how is this data processed? We predominantly run ETL jobs every few hours that extract batches of data from operational systems like MySQL. We transform that extracted data into a data set, for example, GMV per shop, and then load that into a database for analysts to issue queries against and create reports upon. The batch jobs that we run in our warehouse are written in Python on top of PySpark by our analysts, one of which former analyst is in the audience. The number of these batch jobs, their implementations, and whether a job reads a specific data set or not changes really frequently, making it difficult to keep an up-to-date picture of how all of our data sets work in one's head. How frequently do they change? Well, we have over 100 developers in this one repository making changes to over 3,000 jobs, and on average we deploy about 15 different versions of these jobs each day. And the engineering team that I work on not only maintains the platform and frameworks that these jobs run on, but also helps our analysts maintain their jobs and the integrity of the data that they produce. And to help make sure that these jobs are working, and to see which jobs or data sets are affected by various platform-related bugs that pop up, we need to be able to navigate this ever-changing set of jobs, their implementations, and the relationships between them to debug issues. So how do we do that? One way that we do that is through a Django app called Hue. It's a very handy way to visualize groups of jobs, which we refer to as flows, and the jobs themselves. Hue can show lists of jobs that are completed or being run by our scheduler, Uzi. And Hue is a Cloudera product. We didn't build it. But one downside to using Hue is that we can't search by all of our job metadata. We actually have a lot more than we put into our scheduler, like where a job reads or writes from, which team maintains it, how often it runs, what resources it uses, etc. And this can be an obstacle when we're trying to explore our jobs, understand how they're related, and break them down by their properties to see if a bug applies to them or not. So how can we gain access to more metadata to search through? Well, all of our metadata used to schedule our jobs is contained within a set of YAML files in a Git repository, alongside the job implementations themselves. These files are at most 20 minutes newer than what's actually running in production, so they're a pretty reliable approximation for the metadata in our scheduler, and if we really need exactness, we can check out the exact Git SHA. And we can search these YAML files to learn more about our jobs. Here's an example of what that YAML looks like. This is the gross merchandise volume flow group of jobs that I showed you a graph of earlier. And this group of jobs runs every 2 hours. It has a team that owns them. There's a compute GMV job within this group. It uses a lot of resources, a XX large resource class. It's implemented by a specific Python script. It takes an orders dataset and a transactions dataset as input, and it outputs a dataset on GMV. And there are a lot of other jobs in this group that are part of this flow, for example, the extract orders job, but they're not shown for brevity. And using an editor, we can browse this YAML to view metadata, but except for finding details for specific jobs and some basic aggregate statistics like using your editor's find functionality and trying to see the number of occurrences of something, there's not a lot of analytical power here. And remember that we have over 3,000 jobs that consume each other's outputs. So when we find a bug, they usually apply to a set of jobs that all that all share some similar properties, and we need to be able to query our schedule to identify these similar jobs, find all the data that is produced directly or indirectly by them, and fix both the jobs and sometimes their data. YAML has the metadata we want, but it's not laid out in an easy-to-consume way when we're concerned with many jobs at once. What we really want is to view our job metadata as a table. That way, each row consolidates all information about a job, and if we were able to filter this table by its columns, then we could find groups of jobs that share similar properties. And thankfully, we already have some Python YAML parsing code laying around in our to schedule our jobs. So we reused those parsers and made a script to generate that table that I just showed you. And all the script does is parse our schedule and prints to the console one row of tab-separated values at a time. I can't show you the actual schedule that we use, but I can show you an automatically generated one. And if you visit the Git repo link at the bottom of these slides and follow along if you like, you can see all the scripts that I'm running. And here's what I'm showing you now is a snippet from the jobs.py script. It just iterates over, as soon as we've parsed that YAML, it iterates over each flow or group of jobs, and then each job within. We're just printing the job name, the resources it uses, or the job name, how often it's run, the frequency, the resources it uses, and its output. And there's a lot of other metadata that we could print, like the owning team, job implementation file inputs, etc. But I'm skipping that for brevity during this presentation. And this will print the information that I just showed you in the previous slide. Note that I'm printing the flow name and frequency repeatedly. So abiding poetry shows up a lot, and so does 6. Once for each of the flow's jobs, because a flow is a parent of jobs. If this were a database table, it would be bad to design a denormalized table like this. We'd have a flows table and a jobs table, but in the terminal, pre-joining like this makes filtering jobs by properties that they inherit from flows easier. Have any DBAs walked out of the room yet? Denormalized tables are your friend on the CLI. So what does this table look like when we script it? Well, not bad, but also not great. It's a little hard to distinguish columns. Is there anything that can help us pretty print this table? We could change our Python script that I showed you, just iterating through that loop, to format our columns with variable whitespace so the table is nice and easy to read. And there are some great libraries for formatting output like this, Tabulate, for example. But let's keep our script simple and just output tab-separated values. It's currently making an on-demand TSV file for us, essentially, and writing it to standard out. There must be some Unix tools that can take advantage of this. And yes, there is. There's a handy little tool, for example, called column that we can use to format our output, or format our whitespace for us. All we need to do is generate our output and then pipe it to the column program like so. And that's slightly better organized. And look at that, we have a nicely formatted table that we can look at. But what was that piping wizardry that I mentioned? Pipes are the glue that Unix-like operating systems like OS X provide you to combine programs together by passing output between them. So here's the command that I just ran. It's generating tab-separated values with that Python program and passing them directly to the column program, which then prints them to standard out, which we see in our terminal. This chaining is called a pipeline. And roughly how that works is Bash creates a special in-memory pipe file in the pipe file system. It then forks twice, giving us 2 child processes, one for the Python program, one for the column program. Bash then sets Python standard out to the right end of the pipe file. The standard in, it sets standard ins, then sets column standard in to the read end of that same pipe file. And then both processes start to run roughly in parallel, reading and writing from that pipe file, blocking on write when the pipe file is full, blocking on read when it's empty, stopping when they're done writing or reading output. And that lets us create a really simple Python script that creates raw tab-separated output, and we can pipe it to other Unix programs to massage into whatever form we desire. By keeping the output simple, we don't narrow the possibilities of what we can use this output for. We make our script do that one thing really well, create tab-separated metadata. And the best part about relying on pipelines to adjust our output is that we get to spread our work over multiple concurrent processes without writing any Python threading code. Now, all I've shown you, though, is how to show a table. That's still not very useful for navigating a warehouse of 3,000 jobs. What other tools are available to us, and what can we use them for? Well, for starters, if we want to throw some columns away, there's a tool called cut. We can use that to take our large table and narrow it down to just the columns that we want. For example, I can say if I just want the flow name and job name, I can say just give me the first and second columns. And there we go. That's still, so far, just a display-related tool. What about some real, actual analytics? What about filtering? How do we answer questions like, which jobs use the large resource class? Well, for that purpose, we can use a tool called awk to filter rows and only print them if they meet certain conditions, such as whether the fourth column contains the string large. And there we go. Now we're beginning to list only large jobs. grep you could also use for filtering, but with variable size columns, awk is a little easier to work with. Now that we have filtering, what about some aggregate statistics? Can we count? Yes, we can. Using the word count program, we can also pipe our previous filtering to it and find out that there are 102 jobs that use the large resource class. And some of these calls produce a lot of output, and sometimes you're going to do something very expensive with that output later in your pipeline. Like this is pretty cheap, but some things are not. So it would be helpful if we could just pass a short bit of our output through a pipeline to prototype it. For that, we can use a tool called head. I'm going to slightly alter the command that I'm running, if you notice. Oh no, I got a little bit of that table, but there's a large garbled stack trace. What happened to our table? Well, getting rid of some of the output, we can see that what we got was a broken pipe error. That happened because head does something special when you pipe to it. Head is reading from the pipe file all the output from the Python script up until it sees, in this case, 10 lines, and then it closes the read end of the pipe file. But our Python script doesn't know that head has had enough, and it still wants to write more output to the right end of the pipe file. If the Python script tries to write output to that pipe file, and the OS has closed it, then we get back from the OS an epipe error, which Python wraps for us as a broken pipe error. Thankfully, though, the OS provides us a way that we can tell that we should stop writing before this happens. That's called a signal, in this case, sigpipe. When all file descriptors pointing to the read end of that pipe have been closed, our Python script is sent sigpipe, indicating that the pipe that we are writing to is closed and we should stop writing to it. And all we need to do in our script to handle this is write and register a signal handler that closes the right end of our pipe file, in this case standard out, and exits the program when we receive it. And now that we fixed that, what are some other Unix tools that we can use to use these tables and find types of jobs? Well, there's a sort utility that we can use to sort text by entire rows or by columns, which can even reinterpret text as numbers. So, for example, if I was trying to find out what are the most frequently run jobs, sort the frequencies in the second column. So I can say sort, and then I want the second column, and let's interpret that as a number. And then just pipe that to head, just get the first part of it. And there we have it. This is the start of the list of the most frequent jobs with a frequency of 1. Now we could have done this sorting very easily just by using the sorted function in our Python script, but that can be costly because it needs to see all of the output, and sometimes we don't need sorting. For example, when we call head. So I'm going to argue that we shouldn't add to the Python and maybe instead rely on a Unix tool to keep our Python script simple and focus on making it do just one job, leave sorting to another program. Now that we're sorted, how about removing duplicates? Well, there's also the unique utility, which can take sorted output and it can filter out duplicates, which we can then use to answer questions like which resource classes are used in the schedule at all. So resource classes are in the fourth column. So I can say, just give me the fourth column, sort it, and then give me all the unique entries. Oh, well, looks like everything is used. That wasn't incredibly useful. But unique can also tell us frequency counts of any duplicates that it sees. So now we can get a picture of what is the most commonly used resource class in our schedule. It looks like we've got a pretty healthy spectrum of resource class usage there. And both unique and sort are really useful on their own, but where they really shine is in an application that I'll show you next. But before I get into that, I want to talk about another type of table that we can generate. So far, we've been filtering a table of jobs, but these jobs have output datasets, and those outputs are often consumed by other downstream jobs that produce their own output datasets. For example, as shown in this graph, orders and transactions datasets feed into a GMV per shop dataset, which itself is loaded into a database, creating another instance of this dataset. And graphs like this are useful because we can use them to assess the impact that a mistake in producing one dataset would have on everything downstream of it. For example, if we accidentally miss some orders, there are two downstream datasets that are either directly or indirectly impacted. If only GMV per shop incorrectly produced data, then we only have one single database to worry about. And we can represent these relationships in a tabular form with one row per path through the graph, using path starts and ends as columns, and that generates a lot of rows, but it allows us to capture not only direct, but indirect dependencies between datasets in a table like I'm showing you down below. And from a table like that of path starts and ends, we could then use awk to ask which datasets are downstream of this bad dataset, using the code shown below. And this would filter all rows or paths that have a start equal to the bad dataset, give us all affected downstream datasets in the end column. Great, now we can find everything impacted when a single job outputs bad data. But now let's imagine a more alarming scenario. What if we had many bad datasets all at once? What if we had a bug, and we first had to figure out which jobs the bug applied to of our 3,000 jobs, and the datasets they produce, and then which datasets are downstream of that large set of datasets. As an example, let's say that we identified a bug in our software where jobs that don't use a lot of memory and that we run frequently somehow lose data. Let's also say that we've narrowed down the bug to the small resource class jobs and those that run more frequently than 7 hours. We can use awk to filter out jobs, filter the jobs table to only show those that match those two conditions. And that gives us a list of bad jobs and their datasets, but it doesn't tell us what is downstream of all those bad datasets. We need to join this bad dataset list against the list of downstream datasets that I showed you earlier. Is there a Unix tool that can do that for us? Yes, there is. We can use the join command to perform an equality join between two files. It's an incredibly simple tool. It requires that your data is pre-sorted by the column that you want to join on, but it produces one row for each pair of lines that have a matching column in two files. For example, we can take these two files at the top here, join them on the first column of each file to produce the result below. A is in both files, so join emits a row A1. B is in both files, so join emits a row B2. B is in the second file again, so it also join also emits a row B3. C is only in one file, so it doesn't emit a row, and same with D. If instead of letters and numbers we had bad data sets in the left file and paths in the right, we could join these together and get a table with two columns, bad data sets and each data set downstream of them in the end. So let's do that. First, let's get a sorted list of our bad data sets. This is the table that we're working from. If we were to use awk to filter them, we'd say everything less in the second column, everything less than 7, and in the fourth one, it has to be a small resource class. What does that look like? Yep, our query appears to be working. Let's save that as a file called A, which is slightly cut off. but A shows this contents. But in that A file, all we really needed was the final column, the actual data set that's being read, and we wanted it sorted. So let's cut it and then sort it and then throw it into another file called B. What does B look like? Now B just has a sorted list of data sets, and so what this represents is the list of data sets that are affected by our bug where we're running jobs very frequently and using a small resource class. And there are 51 of them at the moment. Now, let's get a sorted list of path starts and ends, what we don't want to join against. This is what that table looks like. And we'll do the same thing. We're going to sort it, and then we'll store it in a file called C. What does that look like? There we go. So we've got the upstream data set on the left, sorted, and then everything downstream of that data set, the path ends, on the right-hand side. So now let's actually join these two together. So using the join command, we can say, in the first file, I want to join on the first column. In the second file, I also want to join on the second column. And the -t basically says, I would like you to insert tabs for your output because we want to do some other stuff with this joined table afterwards. And the two files I want you to join against are called B and C. B being the bad data sets, C being the sorted list of everything, that downstream table. And put that into a file called joined. And what does that look like? So on the left, we can see all the bad data, all the data sets coming from jobs that we identified as bad. And on the right-hand side, that's everything downstream of them. So now we have that list of everything that's affected. There are duplicates in this list, though, because two bad data sets could affect the same data set. So let's filter those out and combine them with the bad data sets, again, to get a total list of absolutely everything we need to worry about. Because bad is only in the left column. We haven't added the bad data sets to the right column. So let's take our joined output. Let's just take the second column. That's everything that's affected. We'll put that into a file called D. And then we'll take that file called D. We'll load it and the bad data sets, sort them. So sort will actually load those two, concatenate them together and sort them, pipe it to the unique program to filter out duplicates, and we'll call that affected. And that, if we count that, means that we have 514 data sets that are affected by this particular issue where we're dropping rows. That started from just 51 bad jobs and bad data sets. And if we were to look at the total number of jobs that we were looking at in our schedule to begin with, 590, that's really not good. That means that around 85% of our warehouse is in a bad state. And there you have it. There's a way to generate some metadata tables about jobs, data sets, using a simple Python script, and how to use some Unix tools to filter and join those tables to answer some real questions about a data warehouse. And so why do we use this interface to do impact assessment? This can't be the easiest way to do this, and you need to learn a lot of commands. So going back. So that's how you would actually get a SQL-like interface on the command line using Python and some Unix tools, and how you could navigate a data warehouse using that. And what I showed you is an artificial scenario, but all the principles are the same in the version of these scripts that we actually use day to day. And yes, why do we use this interface to do impact assessment? This cannot be the easiest way to do this, and you need to learn a lot of Unix commands in addition to do that. That's solely my fault. A while ago, I took an interest in kind of developing a minimalist programming experience for myself, moving from Eclipse all the way to VI and Emacs, from relying on my editor to tell me about a software project to instead using Unix tools in the CLI instead. and trying as much as possible to only interact with the CLI when developing. I originally built these scripts and learned to use these tools to supplement my own dev experience, or dev environment, and because it was fun. But then late one night on Slack, we needed an answer to the question, how many datasets are affected by this incident? And we need to know with precision. And I grabbed the tool that I had on hand, shared it with others, and we liked it. So now instead of writing bespoke Python scripts to find jobs affected by an issue or a bug, we now have a set of prepared scripted tables of metadata, so there's no more reading someone's untested code at 1 a.m. to figure out the list of affected jobs. With a git SHA, these tables, and with these Unix tools, provide a reproducible way to analyze our schedule that doesn't rely on one of the systems we're debugging, which is also not helpful. So to summarize, I showed you the benefit of keeping your Python script really simple, and instead of adding features to it like sorting, or being able to cut or remove certain columns optionally, or truncating your output, I suggested leveraging the power of a few Unix tools to make the most out of tabular output. Those tools being head to truncate, column T to pretty print, grep-a-doc for filtering, word count to count sort, unique to not only dedupe but also count frequencies, and join to actually join on some sorted files to answer some quick questions. And there are so many more that I didn't discuss. But that's most of the time that I have, so check out the repo link below if you want to get these slides and play around with some of these scripts. And thanks for listening.
We have a few minutes for question if anyone has a question.
Hi.
Hey.
Sometimes these tools are inconvenient because they process lines, like streams of lines of bytes, but sometimes your source is already like a nice JSON object. Do you have some tools in your toolbox which are nice to know for this kind of processing in the same philosophy?
No, I do not. I don't deal with too many JSON files, but except for when it comes to reading Python tools, or reading JSON, or at least pretty printing it on the command line. What is that called? JSON tool. Yes, someone knows what I'm talking about. And then the actual file itself, that's a great way to pretty print JSON files on the command line, because in a lot of systems you're working with, it'll just give you a blob without any new lines. This will actually pretty print it and show you the structure. As for getting into a row-based format, I haven't done that yet, but if you code that, I would love to see it and use it.
There's a tool called JQ.
Oh.
That you pipe JSON into and you can do queries.
Oh, really?
Calculations. It's like the XSLT of JSON.
To repeat that, there's a tool called JQ that can essentially that we can use to query JSON. I will have to look that up later. Thank you.
Any other question? Thank you, Chris.
Thank you.